Hello AP Calculus students, Mr. Gilson again. Today we're going to talk about sigma notation and integrals. So we know about integrals and estimating integrals with Riemann sums. We know that integrals have their own notation, something like this. And we know that when we compute Riemann sums, it ends up looking something like this. Where we're thinking of the Riemann sum as being a bunch of rectangles, where each rectangle has a height that is f of x, and it has a width, which is delta x. And there are different x values that we substitute in for each one of the rectangles, and each of those individual x values computes the height of that specific rectangle whenever it's evaluated in f. Well, sigma notation is just the go-between between these two. So if you understand how this is like that, then you'll be able to understand how we go between those. That is, you'll be able to understand sigma notation. So relating integrals to Riemann sums is easiest to do if we imagine the Riemann sum is computing the area under a curve. But we have to be given some details about how that area is to be computed. So let me give you these details for this problem. So in this case, we're going to use 3 subintervals, and we're going to compute using a right edge Riemann sum. It's easy to imagine what those individual rectangles look like. So here we see the 3 subintervals. We see the overall interval, which is 6. And we see that we're computing the area of these rectangles by using the right edge of each of those rectangles. So we can write a Riemann sum that approximates this integral. So a Riemann sum like this is pretty much a no-brainer. But we'll start with a simple example to learn how to work up to sigma notation. Now, right now, this is very specific to this equation, but I want us to start generalizing. So let's start with delta x. How does one determine delta x? Well, how did you determine delta x in this case? Did you just take the difference between the upper limit of integration and lower limit of integration, which is 6, and just divide it by the number of subintervals, 3? That's exactly what you did. So I'm going to add some notation that is not typical in sigma notation, so just follow me. I'm going to add a variable that usually is not used in sigma notation. And I'm going to call this variable capital I. And all that it is it's the width of the interval on which you're integrating, or the interval on which you are summing. So in this case, I is equal to 6. It should be clear to anyone that I is always going to be equal to b minus a if we think about the integral written in standard form, with the lower limit of integration denoted as a and the upper limit of integration as b. Although we're using a very specific example, I want to start generalizing our notation. So the integral I'm going to write as the integral from 0 to 6 of f of x dx. Now we understand that f of x is x squared, so if we were actually doing computations, we'd be able to compute f of x. But for notation's sake, we're going to try to stay as general as possible. So think about this. So in this case, there are 3 x values that we're using to evaluate this function in order to produce the 3 terms of the Riemann sum. And I'm going to call those x values x sub 1, and x sub 2, and x sub 3. That shouldn't be a big stretch for anyone. And instead of 2, I'm going to call that delta x. Well, that's consistent with the notation we've used in the past, but let's go even a step further. I want to define a variable, and I want to define a variable n. And I want n to be equal to the number of subintervals. That's going to be important to us. So that n becomes important because of the way that you computed delta x, or the width of each interval. How did you compute delta x? Well, you took the interval width I, and you divided it by the number of subintervals n. So in this case, the interval width was 6 units going from 0 to 6, and the number of subintervals was 3, so that means delta x ended up being 2 in each case. So let's include that now in our more general statement of the Riemann sum. So here, delta x is being replaced with this expression I over n. We're just trying to make this as general as possible, and it's going to be important to the sigma notation that we finally settle on. Now, although x changes from one term to the next, the delta x remains the same every time. It's I over n. Now let's do more to investigate the values of x that you selected. You had no trouble choosing those values, so obviously the way of getting those values is very simple. But you do have to look at the most general notation to recognize it in sigma notation. So let's think about, how did you decide what the first x would be? You decided the first x would be 2. Why? Did you take the beginning of the interval, 0, and just add 2 to it in order to find that value? No, that's exactly what you did. So I'm going to put that in our notation. And how about the second x value? How did you determine that? Well, whether you were fully cognizant of it or not, you were taking the left edge of the interval and you were adding 2 plus another 2 to get to 4. Does that make sense logically? So that's what we will put in place of x sub 2. And it should be very straightforward for you to complete the rest. What is the third expression going to look like? Yes, 0 plus 6. Now, I want us to represent this relationship a little bit differently. So in reality, when you were computing those x's, weren't you computing 0 plus 1 times 2, and 0 plus 2 times 2, and 0 plus 3 times 2? For each individual element in the Riemann sum, you just multiplied the subinterval width times whatever term it happened to be. The first term was 1 times 2. The second term, 2 times 2, 3 times 2, and you can imagine that that could go on. Now this value, this 1, then 2, then 3, and continuing if there were more elements to the Riemann sum, that's called a counter. Should make sense. You've got the first term, second term, third term, and the first term has a 1 in it. That's the value of the counter. The second term has a 2 in it. That's the value of the counter. The third term has a 3 in it. That's the value of the counter. And you can imagine that if there was a fourth term, then the counter would have a value of 4. Now this is important because of the way that it relates to sigma notation. So now it's time for the real deal, sigma notation. So first off, when we use sigma notation, there's a reason we call it sigma notation, because it all revolves around Greek letter sigma, which is S, and it represents sum. So look at what we're doing in this Riemann sum. We're summing things up. Now what are we summing up? Well, we're actually summing up terms that are remarkably similar, aren't they? They're really following the same pattern. So in sigma notation, what we do is, instead of writing out the 3 individual terms, we write the term once in sigma notation, and then we just say, hey, use this relationship 3 times, and here's what it looks like. In this case, we're summing up this f of x, but the x has some structure to it. It's 0 plus k times 2 times I over n, which we know happens to be delta x. Now, how do we tell someone, hey, we want this to be counted up 3 times? Well, I put in that letter k as a variable for the counter. And in sigma notation, that's very common. And we're going to always start at the first of those intervals. And how many are we going to sum up in this case? We're going to sum up a total of 3. And so I'm going to put n equals 3. So this tells us how many intervals there were. how many subintervals there were. And that's the same n that we used here to compute the width of each subinterval. So just a reminder, k is a variable that just means a counter. K always counts from 1 to some higher value. At the top of the sigma notation, we put the highest value of k. So this can tell us how many individual terms we're adding together. In this case, there are going to be 3 terms. To the right of the sigma, we have the argument for the sigma notation, and this is like an equation. This equation is going to always follow a pattern like this, which we'll investigate more in a moment. And in that pattern, there's a counting value that changes over and over and over. In this case, it is the coefficient in front of the 2, the width of each interval. And what we're telling with this sigma notation is that you're going to do this, or you're going to evaluate this expression 3 times. The first time, the second time, and the third time. And when you get to the third time, you stop. So the whole point of sigma notation was to be kind of this interface between Riemann sums and integrals. So what we've written here in the sigma notation, we're going to call is an approximation for some f of x dx evaluated from 0 to 6. In this case, with 3 subintervals. Now you have to be given this information in order to write a sigma notation or a sigma term for a Riemann sum. So we're going to work just a little bit more to generalize this sigma notation a bit more. Now consider this delta x. You computed by computing I over n. That is, I was the width of the interval. In this case, I was equal to 6. And n was the number of subintervals. In this case, the number of subintervals is 3. So that gave you 2 as your delta x. Well, that is exactly the same delta x as that 2 was. So let's make that substitution into the sigma notation to flesh it out so that it is becoming just as general as it could possibly be. So now our sigma notation looks more like this. So we're getting close to finalizing our sigma notation so that we can start relating Riemann sums and integrals using sigma notation. Let's start with the sigma, meaning we're summing something up. We're going to use k every time as our variable for the counter, and we always start with the first, and we end up at the, well, let's wait on that one, but n equals something. And we're going to be doing what? We're going to evaluate f. We're going to evaluate it over and over and over using different values of x. And how are we going to find those values of x? Well, we're going to take the lower limit of integration, and then we're going to add over and over and over the interval width. We oftentimes refer to it as delta x, but in this case, we're going to refer to it as I over n, and then that's going to be times delta x, I over n. But we can generalize just a tad more, and let's do so. The last generalization is to relate I to the limits of integration. Can you make that change? Yep, it's going to be b minus a to compute the interval width. So voila, here is sigma notation that represents that. Now notice I'm using approximation, because in fact if you're integrating, how many individual Riemann rectangles can you imagine are required for true integration? It's an infinite number. Or in other words, n has to be equal to infinity. Well, hang on a second. I could do a calculus problem that even if it had 100 subintervals, I could do the computation. But an infinite number of subintervals, it's not happening. So how do we work around that? Well, it's a workaround we've seen before. Conceptually, I suppose we could just take the sigma notation and put n equals infinity at the top of the sigma notation. That's not an unreasonable idea, but it's not actually the way the computation's done. So think back in calculus. When or what kind of calculation did we use when we said, oh, we're going to get really, really close to something even though we can't quite get there? We're going to get really, really close to infinity even though we can't quite get there. We use limits, and that's our way out here. So we don't put infinity for n. Instead, we say, you know what, this whole thing, I'm going to take its limit. And I'm going to take the limit as n approaches infinity. And when we do that, we take off the little equal sign on the end. So that is a full-blown example of how integration relates to sigma notation. Now, I know it looks like a huge mess like right now, but after you do a few examples with me, you'll figure it out, you'll understand how it works. So let's jump into some examples, starting with our original example. So let's first write sigma notation for the original Riemann sum that we used at the beginning of this lecture. So we were summing up. Now, what was f? Well, remember, f of x was x squared. So instead of just saying f of, instead we're going to say, oh, well, whatever x is, it's going to be squared. And it's going to be multiplied by whatever the interval width is. Because remember, this broke down to a height and width computation like you're doing the area under the curve. So let's start with the width. That's the easiest part. So what is the width? Well, b minus a, that was 6 minus 0, where it was 6, divided by what was in 3. And what values do we put in? Well, the initial value that we put in was 0. And then each time that we moved to the next value, we added another 6 minus 0 over 3. And then k was our counter. So that instead of writing out the three separate terms, we're going to use sigma notation and say, well, we're going to start with k equals 1, that very first term, and then we're going to keep adding until we get to n equals 3. And when we get to the third term, we stop adding. So what does it look like in simplified form? So here is sigma notation to represent that Riemann sum. So let's make sure that we understand how it represents the Riemann sum. So when we look at this k equals 1 and n equals 3, that means there are a total of 3 subintervals. We know that we start with the initial value. This is really the lower limit of the integration, or in this case, lower limit of the interval that we're computing the Riemann sum on. This 2 and that 2 both are the width, or delta x, for that specific Riemann sum. K was the counter. We do the first term in the Riemann sum, and then the second term and the third. And the function itself is x squared. So notice, everything here really is an x quantity. So could we say that the integral of x squared dx from 0 to 6 is equal to this Riemann sum, this sigma notation? And the answer is absolutely not. Because in this case, this sigma notation is representing a finite number of intervals and a very specific value, at least starting value, for x. So let's look at what it takes to make it equal. Right now, if we were to do this, we could only say that this integral is approximately equal, okay? If you'll notice in the previous lecture slides, I was careful to put approximate because it's not quite the same. So let's look at how you would write actual integrals as sigma notation, and then we'll reverse the process. So when we're writing sigma notation for an actual integral, we can't have the specificity of starting at a specific or having a specific value, having a specific number of intervals, and so on and so forth. So what we have to do is we have to first set up the sigma notation. So we know it's going to be a limit as n approaches infinity of something that we're going to do over and over and over. We're going to start on the very first one, and we're going to do it an infinite number of times. And what will we be summing up an infinite number of times? Well, for an actual integral, it's actually pretty dang easy. This just basically gets repeated. And the dx becomes delta x. And instead of just using x, we use x sub k. So if you think about it, the sigma notation looks so much like the integral itself. All of this business describes that. But there's one thing that's missing, and that is the limits of integration. So the way that this works is, if you were asked to write a sigma notation for this integral, you'd have to give that notation and then say on, and then you have to give the interval over which it is being evaluated. So there is the lower and upper limits of integration. The idea being, this is general. This would be true for every single x squared delta x. So you've limited it to a definite integral by the limits of integration. So that then begs the question, well, what would an indefinite integral look like in sigma notation? Well, let's do one. So we know that we're going to have an infinite number of intervals whenever we actually integrate. And in this case, we're just going to have to repeat the function. And instead of putting 3x plus 5, it's going to be 3x sub k plus 5. Now, since there were no limits of integration here, then there is no restriction on an interval for the sigma notation. The most common kind of just nuts and bolts sigma notation is you'll be presented something written in sigma notation, and you'll be asked to write it as an integral. So if we think about this, we know that this means that we're integrating. We're having an infinite number of subintervals. We're integrating on this interval, so we know that the lower limit of integration is going to be pi over 2, and the upper limit of integration is going to be 7 pi over 2. And we're going to be integrating sine of x plus pi dx. Now, most of the straightforward sigma notation problems look like this, so there's not a lot going on. The reason that I went through the more full detail earlier was because there is another kind of class of sigma notation problems that require you to think at a much deeper level. So let's look at a couple of those. So here's a problem that's structured like the more challenging sigma notation problems are. If a sigma notation problem popped up on the AP exam this year, I would expect it to be something like this. So let's break it down and do a couple more problems so that you understand it. So let's take ourselves back to the early example. So remember in the early example, the earliest lecture example, we were doing a Riemann sum. And what did that Riemann sum look like? Well, we were taking some value a, which was the initial value of the Riemann sum. We were adding to it some k times a delta x, and then that times another delta x. So that's the equation if we put a sigma out front from k equals 1 to whatever the n happens to be. Okay? So finding this structure in the problem is of utmost importance. If you can find this structure right here, then you can do the hard problems. So let's try to break it down. Let's flip these two before we do. So if you recognize this is going to be a definite integral, we can start trying to pick up the bits and pieces of the definite integral. So first of all, you should know the lower limit of integration on the definite integral is going to be 10. You know k is the counter, so it doesn't really mean a lot to us, but this 3 over n has meaning. Now what was 3 over n? Remember, that's delta x. And think about the problem at the very beginning, the Riemann sum. How did you compute how wide delta x was? Well, you took the width of the interval and then you divided it by the number of subintervals. Remember, in the early problem, the width of the interval was 6 because the integral went from 0 to 6. Well, we can deduce that out of this problem too. So that 3 over n is really that interval width divided by n, because that's how you find the width of delta x. So that tells us that we're integrating some f of x. Now, we don't know what f of x is, but we do know that it's a definite integral that's starting at 10 and has an interval width of 3. Interval width of 3, that means it goes from 10 to 13. So if you understand the structure of the sigma notation, you can just deduce these definite integrals. There is no magic potion that you can use. There is nothing you can to memorize. You just have to understand the structure. So let's do a couple of more examples. So you can always think back to that original Riemann sum that I used to introduce sigma notation. Think about that integral from 0 to 6 of, well, it was f of x dx. We don't care much about what the f of x and dx was. And that was equal to, in sigma notation, you had that k equals 1 go up to n. It was a plus k delta x times delta x. If you can take your mind back to that original lecture example every single time, then you can do these problems. So one last little detail on the lecture example, remember? It was just the graph of f of x. F of x happened to be x squared, it doesn't matter. But the important thing is that you remember, oh yeah, if I were doing a Riemann sum, I would determine the width of each one of those intervals by taking I divided by n. Okay, so I know this is going to be a definite interval. I know the lower limit of integration is going to be pi. Now the issue becomes, what is the upper limit of integration? By the way, we know it's just going to be q of x. This doesn't look so familiar. It doesn't look like I over n, but it actually is. So think about this. If I was equal to 2, or pi over 2, and you did I divided by n, that would be pi over 2 divided by n. And what would happen to the n? Well, whenever we simplify that fraction, it becomes pi over 2n. So see, it's a little bit tricky in a case like that, but there is information that gives you, oh, I is equal to pi over 2. Now remember, I represents the interval width of the entire integral. So that means the upper limit of integration is going to be pi plus pi over 2. Or you could write it as 3 pi over 2. Kind of tricky, isn't it? Let's do one last example. So try this one on for size, but take yourself back to that very first lecture example. So if you think back to that lecture example, once again, you had an integral going from 0 to 6. You had it subdivided into 3 subdivisions. So how wide was delta x? Well, delta x was 2. That's because that was I over n, or in this case, it was 6 over 3 equals 2. So apply the same logic to this problem. So we recognize this is going to be a definite integral. The lower limit of integration is going to be the square root of 3. It's going to be w of x dx. Because remember, this is an x value. This was the initial x, and then this is the quantity by which that square root of 3 is being increased from one interval to the next. So now the issue is, what is the upper limit of integration? Well, if you remember, I over n, in this case, would have to be 7 square root of 5 over 2n. Now, I'm doing this algebraically so that those who are more comfortable with the algebra can work it out. So what do you do in a case like this? Multiply both sides by n. That gives you I is equal to 7 times the square root of 5 over 2. Now, what is I? Is that the upper limit of integration? 7 square root of 5 over 2? The answer is no, that's not the upper limit of integration. Remember, that's the width of the interval on which this function is being integrated. So then the upper limit of integration is going to have to be square root of 3 plus that interval width. So I think this gives you enough that you should be able to tackle any sigma notation problem that you would see on the AP exam.